I just realized it's not recorded. It hadn't recorded anything so far. So, all right. All right. So as I was saying, in the previous half-wave rectifier, we can see that the average value, average DC value of the waveform is far lower, right? Because we are losing, we don't have the rectification of the negative half cycle. And so we need to rectify both halves of the cycle. And if we rectify both half of the cycle, we come to what is known as a full wave rectifier. A full wave rectifier. And these are not as well, these were popular for a while, okay, but these are not as prevalent now. So this full wave rectifier, and let me show you with a. We won't talk about the capacitor or the resistor right now. I'm just going to go over the basic operation, okay? So in this full wave rectifier, what we do is we have a circuit, and I'm going to modify the circuit such that it's going to make sense. Okay. How many of you have seen a wall wart? Just one. How many of you know what a wall wart is? Okay. Wall warts are nothing but like your what we now call them as our battery chargers, like a cell phone chargers and a tablet chargers and all. So in the back in my day in the 1800s, we used to have these adapters. Now these adapters would have small transformers inside them, right? So the first thing I kept saying, the first thing every power supply has is a diode at the front end. Well, there was something else before the diode, which was a transformer, because our power outlets are 120 volts, 120. If we want a 15-volt DC output, we first need to reduce that 120 volts down to some manageable level. So that 120 volt would be stepped down to something closer to 15 volts. And what allowed us to do that was these transformers. Transformers, if you studied, if you remember from EE 212, based on magnetic activity, right? You have two inductors wound around the same core. Depending on the number of turns, the turns ratio on the primary coil and the secondary coil, you can either have a step up or you have a step down transformer. Okay. Yes. Uh, these are technically, well, okay. Question being asked is why do we not use op amps? And why do we use transformers, right? Transformers are used to step up or step down the AC voltage, not for op amps are used for amplification of signals. But amplifiers of any kind, okay, this is a very, very important question in terms of fundamentals or fundamental concept. In terms of amplification, meaning you want to provide a gain to an AC signal, the energy to amplify a signal does not come from thin air. It comes from your DC source. So an amplifier, like an op amp, is going to take an AC signal, which is small, and is going to mix it, so to speak. It's going to mix it with energy from a DC source. So the DC source provides the biasing, and then your AC is, well, now amplified. Okay, so they are, it's a good question, but they are two different things. So again, transformers are very crucial. Actually, they are the most critical element outside of the generation in terms of power transmission. So when we transmit power over long distances at the power station, they generate the electricity using a generator. And the generator voltage is then stepped up to hundreds of thousands of volts. Okay, so power is transmitted over long distances over like 10, 15, 20,000 volts. Very, very high voltage. Going on a little bit of tangent, but real practical application. Why is electrical power transmitted over long distances on high voltage? All right, anybody? Less loss on the lines. How and why? Perfect. You all know your stuff, right? And so if we increase the voltage at the front end, well, I would say the back end, then at the front end, when we get to consumers, we need to step it down. And the only way to do that would be using transformers. So we step down the AC voltage and we come back down. I don't think, I mean, if it's like a lower power application, we could perhaps use a different kind of circuitry. But if you're just talking pure AC voltages, if you want to step it down, then that's what we do. Yes. Mm-hmm. Sure. Sure. How would they both balance out, right? Because it's V square or R and I square times R. So it's a good question. So usually I used to do this, but let's go back here. So when we transmit power over long distances, anybody remember the equation for resistance in terms of physical quantity? Rho L over A. And if you have a piece of material made out of any material, rho is the Greek letter rho, R-H-O, stands for resistivity. That is a material property of any material. Okay, within a reasonable amount of temperature, which basically just let's say room temperature, that resistivity is a near constant. Okay, unless we're talking about extreme temperatures. But let's say room temperature, resistivity is a constant. It's a material property. So if you pick up gold, it has a specific resistivity. If you take glass, it has a specific resistivity. If you take silicon, it has a specific resistivity. That does not change. What can change and does change is the length and the cross-sectional area of a material. So theoretically, if I take a cable like this, length is about 6 feet, maybe 3 feet, 10 feet at most. It's not going to have much resistance. But now if you're talking about L, hundreds of miles long, now it has some resistance, significant resistance. Okay. So over long distances, that resistance is large. P is V times I. In terms of resistance, P is also V square divided by R, meaning the higher the resistance, the lower the power loss. But if it's I squared times R, meaning it's directly proportional to the square of the current as well as the resistance. So when we are transmitting over long distances, power loss occurs. Power loss occurs as square of the voltage and square of the current. But when it's voltage, it's divided by, so it's inversely proportional to the resistance. And when it's, if you're talking about just in terms of current, then it's directly proportional to the resistance. Over hundreds of miles, that resistance is a significant number. And so to minimize the power loss, it's better to increase the voltage versus increasing the current. So you keep the current less and increase the voltage, which is also the reason why the rest of the world has 240 volts. Most of North America is 120 volts. It's the same reason. To have more wattage, you send less current in, you send higher voltage. So power losses are minimized. Good discussion. Okay, coming back to center tap. So center tap, we use a transformer, and in the secondary coil, we tap into the middle of the transformer. And so hence it's known as a center tap. So we're making a connection into the middle of the secondary coil and we bring it out. And so what that does is it splits into two power supplies. Okay. Anytime you have a tap, it's going to create a series connection of power supplies. So the point I was making was the wall warts. Then we had for our adapters and chargers, they had small transformers inside of the front end. Those transformers would plug into the wall. So it would step down the 120 volts. It would step it down to like, I don't know, 20 volts, 15 volts, 10 volts, depending on our application. And then we would feed that step down voltage. So 20 volts is now going into our diodes. And then the rest of the circuitry happens. Then they came up with better circuits with mobile devices. All right. Rooster is growing right there. Somebody on Zoom, please send a message. Just a test message. All right. So it's stepped down. In modern devices, you feel it's very light, right? There's no transformer at the front end. There is a rectification at the front end. It's a half-wave rectifier. So your 120 volts comes in, goes into a diode, rectifies it, filters out, makes the DC and everything. Then it goes into a very high speed small transformer. So it's 600 hertz or something. It's inverted. And now it goes into a 600 hertz transformer. So it's now a very small transformer. We don't have time to discuss all of that, but the transformer size is now small. And so it's lightweight, and then it's rectified again. So inside of modern supplies, first there is a diode, so it's rectifying. So AC to DC conversion happens, and the DC is converted back to AC. And then finally, that AC is again converted back to DC. So if you crack open any of your older chargers, you'll be able to see that. Okay, let's see. So center tap. How does a center tap work? We got D1, we got D2. In the positive half cycle, D1 is on and D2 is off. Okay, so the circuit looks like this. On makes a connection and off. Okay, so on and off. And then these, that's how the polarity goes. And so my current flows in this direction, enters the resistor from the right. So if it's entering the resistor from the right, it causes a voltage drop in that resistor with plus on the left, minus on the right. Okay. In the negative half cycle, it reverses. D2 is off. Oh, sorry. D1 is off. D2 is on. And so my circuit looks like this. Actually, not like that. And the reason it's off is because when it turns, it's going to give you this. And now the current's flowing in this direction. It still causes a voltage drop across that low resistor in the same direction, plus and minus. So now, if I was to draw the output waveform, I would have this is T, and this is my V out. And what do I have? I would have And the reason I would have current and voltage going in the same direction is because the current direction is the same in both. And so both half cycles are now rectified, and hence it is known as a full wave rectifier. Point out this is where D1 is on, and this is where D2 is on. Okay. All right. Let's take a pause while you write it down, think over it. Let me know if you have any questions. Yes. Mm-hmm. So question being asked is if V1 was 20 volts, wouldn't the top be 20 and the negative also be 20? Is that the question? Yeah, that is correct. Yeah. 40 volts. Oh, the 20 that I spoke about earlier? So question being asked is how we obtain the 20 volts or how we separate it? Oh, that's electromagnetics. So it was it covered in 211 or 212? Anyway, in one of those classes, it's covered electromagnetic theory, where you have multiple coils that are interlinked. And so it's the turns ratio. So the number of turns in that coil on the primary side and the secondary side has an inverse relationship. So V1 over V2 is equal to N2 over N1, or proportionality. And so that's where it comes from. So there's no specific value. It's just the number of turns would be designed to give us a specific value. So if you wanted, like, say, 10 volts, then the transformer would be designed to provide 10 volts and 10 volts. If you desire 20 volts, then it would be number of turns would be designed to give us 20 volts. This is a center tap. Okay. When I was a student, this is like more than 30 years ago, I had a variable power supply. That variable power supply had a manual switch on the front. The manual switch, it was a dial, and you could like click, 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 click. It's like a manual switch. Okay. And one day, just for kicks, I opened it up. Just wanted to know what was inside it. And so all it was like an actual switch, a mechanical switch with multiple positions. So it was a single pole, multi-throw switch, circular switch. And it had multiple taps in the secondary coil of the transformer. Okay, there were multiple taps. And so it was the output of the DC output of the power supply was 1.5 volts, 3 volts, 4.5, 6, 9, 12, and 15. So overall, the secondary coil was probably providing an output of like 20 volts, and then there were multiple taps to provide the outputs for intermediate. So you can have a multi-tap transformer too. And now, obviously, we don't have that. We have electronic switches where you can just use, say, electronic or solid state, which you can have like multiple levels. I even remember back in that day, or back in those days, we used to have like fan speed control. It would be like a big box like this that was stuck next on the a power switch board in our homes. And they had like 5 settings. And then again, they had like a big dial, and you could change like a switch dial, like tick, 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 tick. It would change the speed of the fan, ceiling fans. And all it was you're just changing the voltage that was going into the fan. So multiple taps. Let's see what time. It was 3:40. Plenty of time. Does this make sense? Idle diode analysis, just looking at the operation. Okay. Now let's talk about the technical aspects. So let's go back to the half wave rectifier. What do we see here? we see that the average DC voltage or the average DC value is far less, right? Actually, you know what? While you're talking about full wave rectifiers, let's go to the full wave bridge. And then we'll go back to the other one. All right. So center tap obviously is not, those are slightly expensive than a regular transformer. It's cheaper to actually put two more diodes in there and have a full wave bridge rectifier. Okay, and this is something that we did in the lab, right? So you take 4 diodes, create a diamond configuration, and in the diamond configuration, you can have a full wave rectifier without needing a center tap transformer. And this is the de facto design of all power supplies now. Just use a bridge rectifier. Okay. And I'm going to use ideal diode analysis. This is, forget about the capacitor for now, and I'm going to redraw this. Let's see, we have a transformer, 1 dot, 2 dots, 3 dots, 4 dots, 2 diodes facing up, 2 diodes facing down, and then we have a load resistor in the middle, and your input goes in here. Okay, input goes in there. That's how you remember a bridge rectifier. Okay, positive half cycle. What do we have? We got D1, D2, D3, and D4. In the positive half cycle, D1 and D3 are going to be off because we have a plus at the top and a minus at the bottom. So the anodes of D2 and D4 are forward bias. Sorry, anodes are higher, so D2 and D4 are forward bias, and D1 and D3 are reverse bias, so they are off. Okay. Current flows from the circuit starting from the top, enters the resistor from the right, hence causes a voltage drop with a plus on the right and minus on the left. Does that make sense? And now, in the negative half cycle, it reverses. And in the negative half cycle, now D2 and D4 are off, and D1 and D3 turn off. And because D1 and D3 turn off, current starts flowing this way. But because current's flowing that way, it still enters the load resistor from the right, and hence that end has positive output for both half cycles. And so we obtain an output that is fully rectified for both, and hence the name full wave rectifier. And because the 4 diodes are connected in a bridge or so-called bridge configuration, it is known as a full wave bridge rectifier. Full wave bridge rectifier. All right, let's take a pause. Think over it. Let me know if you have any questions. But hopefully you can see why I love ideal diode analysis to quickly analyze any diode circuit. Okay. But you have access to my previous recorded lectures. So